And we are very pleased today to welcome Arnaud Doucet, who is both a chair at Oxford University and a research scientist at DeepMind, someone that everybody knows already, I guess, because he made a very significant contribution to computational statistics, Monte Carlo methods, particle filters, etc., etc., etc. Very long list of papers, very good papers that I'm sure you're familiar with. Anyway, let's start. So Arnaud, you have the floor.
Okay, thank you very much for the invitation. So today I will be talking about diffusion Schrodinger bridge. So essentially, it's about a novel class of a generative model, which is an extension of the so-called denoising diffusion models. And I will show how they can be extended, beyond generative modeling to do essentially posterior simulation or approximate Bayesian computation more exactly. So the talk is essentially a summary of two recent papers of mine that have been essentially co-written with Valentin de Bortoli, who is not CNRS in Paris, my colleague George Janidis, who is associate professor in Oxford, Jeremy Yang, who is assistant professor at ESSEC in Singapore, and Yu Yangshi and James Thornton, who had both PhD students in Oxford. Okay, so basically, I'm just going to introduce the class of generative model known as denoising diffusion model. So this is something that has essentially appeared very recently in the literature over 2 years ago now. And it's really somehow the kind of new player in town when it comes to generative modeling, because it displays amazing empirical performance. So there was in particular, in May 2021, a paper by OpenAI entitled Diffusion Models Beat GANs on Image Synthesis, where they show that that could provide actually amazing results. And this has been further extended by OpenAI, and diffusion models are the basis of their so-called daily generative models that have been released, I think, a couple of weeks ago now. Okay, so really, this method are quite impressive. One of the kind of limitation of these techniques is that compared to GANs, well, at least 2 years ago, they were fairly slow. Okay, so what we'll be doing here is that I will first review the class of denoising diffusion models, and I will show how we can come up with some kind of principled way so as to accelerate them by using tools of optimal transport. That'll be the first part of the talk. And in the second part of the talk, I will go beyond generative modeling, and I'll show how we can also use this type of ideas so as to do inference. Okay. So first, basically, I'm going to kind of review the class of denoising diffusion model. And to review them, what we need to do is first to essentially go back to the element of Markov Chain theory. And so I'm just going to start with a slide, which is Markov Chain 101. And really, what we're going to consider is we're going to consider a strategy where we're going to have some kind of noising process. We're starting from some kind of sample image. I have available in my training data. I'm going to progressively add noise, okay, using this Markov chain. So mathematically, you're going to define a discrete time Markov chain. Initial state is basically coming from, say, if you want to simulate images, you have access to some training data. So it's going to be basically a sample from your training data, and progressively you're going to add noise. Okay, so that's going to define a joint distribution of the state x0, x1, x2, xn. Okay, and I will denote by pk the marginal distribution of the state xk under this forward dynamic. So if you want to sample from this collection of state x0, x1, x2, xn, you can use this kind of forward mechanism. This is the forward sampling. But obviously, what you could do also is you could reverse the arrow of time and use backward decomposition of the joint distribution of the state x1, x2, x1, xn, which is given simply by the marginal distribution of xn at time n time a product of reverse Markov transition kernel that takes you from a time sk plus 1 to time xk. On this backward Markov transition kernel, they are obtained simply using the base rule on the forward transition kernel. Okay, and we'll go back for them later. So what you could say is that really, so as to sample equivalently from the joint distribution of x1, x2, xn, where I can use the so-called ancestral sampling, also known as backward sampling in the kind of computational stats literature. That is, I could sample xn from its marginal distribution Pn at time n, and then recurse backward on what I would obtain at time 0. I should obtain something that is basically distributed according to the distribution of the data. Okay, so that's the kind of rough idea. So you're going to have essentially a process that goes forward that's going to add noise progressively to the empirical data that are available to you, empirical distribution, the sample that are available to you, and you're going to try to essentially denoise them progressively in a kind of backward procedure so as to obtain, starting from noise, you can go back at time 0 to sample that will look like the data. So that's really the kind of basic idea. So mathematically, what do? Well, we need to define a bit more precisely what kind of forward transition kernel we use. We need to see how we could implement really this kind of ancestral sampling procedure practically. Okay, so practically, remember, I have sample from the distribution of the data. This is say CFAR10 or ImageNet or whatever. Okay, really what you do, you use this kind of noising forward dynamic. I'm going to use a simply an autoregressive Gaussian process. Okay, so you're going to have essentially each time I take the current state, I multiply that by alpha, where alpha is inferior to 1. I add some noise, those variants, 1 minus alpha squared time, essentially the identity matrix. And I know if I keep doing that progressively, you know, for a few hundred time step, I'm going to get eventually some sample such that the marginal distribution at time n of my state is going to be roughly a multivariate normal, standard multivariate normal. Okay, so that's my forward dynamic. Okay, so first thing I had to do when I wanted to mimic ancestral sampling, I needed to sample from the marginal distribution at time n of xn, and then simulate from the backward transition kernel, where I can already compute exactly Pn, okay, this kind of marginal forward distribution, but I can approximate that by this kind of multivariate standard normal, because by construction, I know the forward dynamic technique there. Okay, so I can simply make a first approximation in my ancestral sampling procedure, which is to say, well, I'm going to replace Pn, the marginal distribution Pn, by this kind of standard multivariate normal. Okay, so that's the first, and that's the easy thing to do, but we still need to approximate those backward Markov transition. Okay, so how am I going to approximate those backward Markov transition? Well, I'm going to remember that, you know, we're still working simply with forward transition kernel, which are very, very simple. This is just autoregressive Gaussian Markov transition kernel. And you can think of it actually as some kind of discretized Einstein-Riesenbeck process. Okay. Because you add noise like progressively very slowly, well, think of that the kind of autoregressive coefficient in your forward Markov transition kernel is very close to 1, actually, so 0.99. So now you want to approximate the backward Markov transition kernel, where you have an expression for the backward Markov transition kernel, which is given by essentially the base rule. So backward Markov transition kernel taking you from xk plus 1 to xk, well, is the forward transition kernel that takes you from xk to xk plus 1, times what? Times the ratio of the marginal distribution pk over the marginal distribution pk plus 1. So we don't have access in closed form to pk and pk plus 1, but because I had noise very slowly, you know, I have this alpha very, very close to 1, I can make some kind of Taylor expansion. I know that pk is roughly equal to pk plus 1, okay? And I'm just going to make a Taylor expansion, and really you end up with some kind of elementary calculation to finally an expression of this form, okay? So you can approximate the backward Markov transition kernel by some Gaussian density of argument xk, and you have the mean, which is a function, a convex combination, sorry, a linear combination of the state xk plus 1 on the so-called score. So here, this is not the kind of Fisher score. This is the Stein score. This is the gradient of the log of marginal distribution with respect to the spatial component x. There's no statistic called parameter theta here. Okay, so it's just all the gradients you're going to see that appears in my talk are gradient with respect to x. Okay, so at least we are kind of an expression, an approximate expression for the kind of backward Markov transition kernel that appear in ancestral sampling, but we're not done yet because, well, we don't have access to those marginal distribution P1, P2, Pk plus 1, and so on. So we don't have access in particular to their gradient, the gradient of their logarithm. So as to kind of bypass this problem, we're just going to use the fact that, well, okay, we don't have access to this kind of gradient, but we can approximate that by solving a regression problem. And this is the idea behind what is known in the machine learning literature as score matching. So the basis of our approximation is the fact that by Chapman-Kolmogorov, I can re-express the marginal distribution Pk plus 1 of interest as essentially the initial distribution of P naught of x naught from which I can sample, which I have access to n sample, time transported by the transition from x naught to xk plus 1. Okay? On here, because I go from one state to the other in the forward Markov chain using some kind of autoregressive Gaussian, P of xk plus 1 given x naught is a transition kernel, which is very simple. It's a linear Gaussian transition kernel. So I have access to it analytically. Okay, so that's what I'm going to leverage later on. So now, after elementary calculation, you can prove, using this kind of Chapman-Kolmogorov equation, you can prove that the score of interest is given by the expectation of the gradient of the log transition. And this is the expectation in respect to the distribution, the posterior distribution of x naught given xk plus 1. Okay, so this is the expectation of a quantity you know. Okay, this thing you can compute it analytically, the gradient of the log transition, but the expectation in respect to this measure, which is not tractable because this is the conditional distribution of x naught given xk plus 1, you only have access to some sample of x naught. You basically cannot sample from x naught given xk plus 1 exactly. Okay, so how are we going to proceed when we are there? Well, at least we realize now that this is a conditional expectation. I cannot sample from the distribution of x naught given xk plus 1, but it's trivial to sample from the joint distribution of x naught or xk plus 1, because so as to do this, I just need to pick essentially a random sample from, say, my cipher 10, and then add noise to it. So this is really trivial to sample from the joint distribution of x naught xk plus 1. And then I use simply that, well, you can always think essentially the conditional expectation is a solution to some kind of mean square regression problem. Okay, so I'm just going to say, well, okay, I'm going to parameterize. I'm going to consider a flexible set of regression function S. Okay, so particularly I'm going to use a neural net. So this is a function of xk plus 1, and I'm going to essentially simply minimize the expectation with respect to the joint distribution of x naught xk plus 1, which is trivial, of the square error between S and the gradient of the log transition. Okay, and I knew that if I had access, if I would parameterize all the regression function, the minimum would correspond to the conditional expectation of interest, which is the so-called score. Okay, so that's essentially the rationale behind what we're going to do. So practically, we don't have access to all regression function, but we're going to parameterize S by a neural net. Okay? And because we need to do this, we need to estimate the score not only at time, basically because we need to approximate all the backward Markov transition kernel, we need to approximate the score at time 1, at time 2, and so on and so forth. So what we're going to do simply is instead of using one independent neural net to estimate each score individually, we just use a neural net, which is going to have two input, time and space, essentially, and that's going to approximate all the score from time 1 essentially to time n, capital N. Okay, so the way we propose to learn the parameter of this neural net is simply following essentially this formulation of the score as the solution to a regression problem. I'm going to essentially minimize the sum of the square term, okay, over the parameter theta, my neural net. And to achieve that, well, what you can do, you can easily get the gradient with respect to theta using all your favorite autodiff tool, and you can mini batch also over k. So this is kind of actually very practical. Okay, so it's kind of fairly easy to do this. So that's actually quite a lot of engineering that gets into the architecture of the neural nets you use, so as to estimate those scores properly. Okay, but once you've done that, so on to do this, I said it's not quite complicated. You're going to use stochastic gradient so as to minimize such a loss. This is achieved that simply sampling from sample from your database, adding noise to them, taking the gradient and minimizing. Okay, so that's quite easy. And once you learn your essentially the score network, you eventually obtain new sample by performing an approximation of the ancestral sampling. That is, at time n, the final time step, you sample not from Pn, but from your reference distribution, that is the multivariate standard normal. And then you do approximate backward sampling by approximating the backward Markov transition kernel, on where this is essentially taking the expression of the one I had before and replacing the score by its neural net approximation. So that's one way to come up. This is the way essentially those algorithms are derived. They are alternative, essentially derivation of these techniques, in particular based on the evidence lower bound, and I'll come back to that later. Okay, but that's the kind of basis, the basics of this kind of denoising diffusion model. It can be interesting to think about denoising diffusion model not in discrete time, but in terms of actually continuous time process, that is, or in terms of diffusion. Okay, so maybe when you do this, the maths are obviously a bit more tricky because you have to use stochastic calculus, but at the same time, it's more elegant. Maybe you'll see where some of this approximation, where they're coming from. Okay, so in continuous time, if instead of considering that you were having n finite time step and you had noise using autoregressive Gaussian, you could think of it as, well, I basically have a forward process which consists of sampling essentially from the initially I have a state from the distribution of the data, and then I had, well, a continuous time version of autoregressive Gaussian process is what is an Einstein-Weinberg process. Okay, and if you do that, you know that essentially you're going to relax toward multivariate normal distribution. Okay, so that would be the forward process. Okay, so what's the equivalent of ancestral sampling when you're dealing with this diffusion? Well, it corresponds to essentially simulating from the time reversal of this diffusion. Okay, so if I write yt, which is by definition x capital T minus t, where t is the final time horizon of my forward diffusion, okay, then you can show, and this is standard result from stochastic calculus, that the time reversal satisfies this expression. So this is a process that you initialize by the marginal distribution at time t of the forward process. That would be the equivalent of my Pn in discrete time. And then, well, you have the forward drift for this time reversal diffusion, where you see here that what appears is the so-called score again. Okay, so essentially, I had presented it previously as some kind of dirty Taylor expansion obtained from the base rule, but you can have a bit more, rigorous derivation of this expression if you think of it in continuous time. And really, so this is my kind of exact summary, if you want, ancestral sampling procedure. And really what you're doing when you're doing this kind of denoising diffusion model, you're approximating this time reversal process, and you're making two approximations. you instead of initializing the diffusion by the marginal distribution PT, you initialize it by the kind of Gaussian distribution that is targeted by the forward process, and you approximate the score by some neural network estimate. And you can think really that how do you estimate the network parameter, the neural network parameter, where previously I showed it as some kind of bit, a bit with my hand, saying, well, I can think of the score. It's a kind of conditional expectation. So instead, I could basically, approximate that by solving a regression problem. Well, there's a kind of maybe cleaner way to think of this is to say, well, what I could do is that if I write as P the path measure induced by the throw reversal and by Q theta the kind of path measure induced by some kind of parameterized time reversal where I have the score S theta that appears in my drift, then really obtaining the kind of neural net can be achieved by minimizing the KL between P and Q theta, okay? And that corresponds to minimizing this kind of essentially this kind of square difference, which can be expressed in terms of the gradient of the log transition using the score matching identity. So I spare you the details, but there's a kind of very elegant derivation of how essentially we should estimate the parameter of the network, and is a simple elbow argument, which I think is much more transparent in continuous time than in discrete time. So I recommend you to kind of look at that. Okay, so that's nice, all this thing, but for those of you who are familiar with MCMC, you could really be wondering, how can it work, really? Because somehow what we are doing is we are doing this kind of generative modeling by sampling this kind of non-homogeneous diffusion, okay, in finite time, and we're working potentially extremely high dimensional space. So think of it that when you're going to use that for images, the dimension of YT would be the number of pixels. Okay, so it could be easily, of the order 100,000 on the result presented by OpenAI, it's of the order of million. Okay, so you're doing a finite time diffusion in 1 million dimensional space. So you could imagine that there might be some mixing issues arising here. Okay. So what we're going to do is I'm going to propose a kind of a crude analysis of this kind of algorithm. Okay. So this is crude because it is based on a very, very strong assumption, okay, which is that we have an approximation of the score, which is essentially uniformly good in time and space. Okay, so this is not verifiable assumption. But at least this is one of the first results that is available in this literature. So that's a step to our understanding those kind of ideas. Okay, so assuming you have this assumption that you've been able to roughly approximate properly the scores, okay, at all time step, then you can have a look at the total variation distance between the low of the sample you obtained by the discrete time algorithm I first presented, okay, on the true distribution of the data. And you can see that this total variation norm, it can be bounded by sum of two terms. One term, which is the second term here on the right-hand side, which is a term which depends on the score approximation, okay? So we had some term, it's pretty crude calculation because we had the exponential in T. We are down to linear now, that I haven't presented in the slide. On the first term is essentially the term that relates to how fast the forward process converges to the reference measure. But what is interesting is from this kind of analysis is that what it shows is that there's no issue with mixing when really you are simulating this kind of high dimensional diffusion, because the mixing property are inherited from the mixing properties of the forward process, which are the mixing property of the Einstein-Uhlenbeck process, which are extremely well understood on that you can write down explicitly. I refer you to my paper if you're interested in detail. Okay, so that doesn't explain yet why we're still kind of able to do some kind of density estimation, extremely high dimension, given that there are minimax right in the literature and the statistics literature. But at least we know that computationally, it makes sense that we do not suffer from mixing issues, despite generating Markov chain in extremely high dimension on infinite time. Okay. So now it's good. Okay, so we provided some kind of overview on this kind of diffusion model. We've shown that we have at least some theory backing up what those models are doing, partly explain what's going on, far from essentially capturing their extraordinary empirical performance, but they suffer still yet from a kind of serious problem. One of the problems they suffer from is that really you need to diffuse for quite a long time, so that really at the final time of your diffusion, the marginal distribution is of your process is Gaussian, because otherwise, if it is not the case, then even if you had access to the exact backward transition kernel, you would obtain at time 0 through your ancestral sampling something that has nothing to do with respect to the distribution of the data. So here, this is an illustration for a 2D distribution, okay, where you kind of add noise to it. So essentially, it's like a convolving by some kind of Gaussian, adding noise to it. But basically, well, what you see is that at the final time step, really have nothing. The distribution doesn't look like anything like a Gaussian, or even if I use exactly, if I restart from a Gaussian distribution PRF and I have access to the exact backward Markov transition kernel, I obtain at time 0 something that has nothing to do with the distribution of the data. So this is a problem, because really what it tells you is that really you need to go like slowly towards really a distribution that is Gaussian. And then after that, your generative model, it has to do the kind of go this end step in the backward direction, in the reverse time direction, but it takes a long time because it means n needs to be quite large, actually, so as to obtain a sample. So each time, really, you want to obtain a new sample, you sample from a multivariate normal, and you will need to do like n step backward, and it was in the first paper, n was of the order of 100, 1000, so as to obtain good result. Okay, so that's a bit expensive compared to GANs. So what we suggested is to kind of see whether there was a way to improve, accelerate those kind of diffusion model using ideas from optimal transport. Okay. So what we're going to do is we're gonna reformulate this kind of generative modeling problem as a so-called Schrodinger bridge problem. Okay. So Schrodinger bridge, it's a problem that appeared, that was introduced by Schrodinger in the 30s and studied extensively in the probability and applied maths community over the past 50 years. I'm just going to basically here going to give a kind of very crude and short introduction to it. So I'm going to consider the following problem. So we're going to consider the base process. So think of it P of x0, x1, x2, xn. So think of it as kind of the forward density I defined it at the very beginning of the talk. So remember what I was doing? I was starting, there was the density of my forward Markov chain. I start from P0, x0 is the distribution of data, which I can only sample. I have access to a few samples, but I don't know. And then it's given by the product of this autoregressive Gaussian. Okay, so that's going to be my base density, base process. And what I'm interested in doing, in finding, is to find another distribution pi on the same path space. Okay, so that's going to be another density on x1, x1, x2, xn, which is such that you minimize the KL discrepancy between pi and p, subject to two constraints. The marginal distribution of pi at time 0 pi naught, denoted pi naught, corresponds to the distribution of the data. Okay. The marginal distribution of pi at time n, denoted pi n, is equal to PRF. This is, think of it as the multivariate standard normal. Okay. So on the solution to this problem is denoted pi star. So that's basically the distribution I'd like essentially to identify. So I want to find the distribution which is closest to this best process, but which has fixed, original and terminal, essentially fixed marginals. Okay. If I had access to pi star, well, by using ancestral sampling on the pi star density, I would have access to a generative model, because what I would do is I would sample at time n from pi n, but from pi star n, but pi star n by definition is equal to PRF, my multivariate standard normal. And then I would recurse backward. Okay, I will recurse backward till time 0, and I would obtain at time 0 a sample from pi star naught, which by construction is equal to the distribution of the data. Okay, so that's if I could do that, I would have access to essentially, by using ancestral sampling on pi star, I would have access to a generative model. On here, by no means I make the approximation that the marginal distribution of xn on the p is equal to PRF or approximately equal to PRF. Okay, so that's the kind of key difference. I do not need to make this approximation. Previously, we've seen that we were using this kind of ancestral sampling, but we were always assuming that the marginal distribution of xn under p was approximately equal to PRF. With this kind of Schrodinger bridge, if I could solve this problem, I wouldn't need that. But in particular, I wouldn't need to have to diffuse too long in the future, and yet I could essentially come up with some kind of valid generative model. Okay. So how is it related, this kind of Schrodinger bridge problem, to optimal transport? Okay, so first of all, by the standard decomposition of the Kullback-Leibler discrepancy, it is easy to check that pi star, the kind of solution, the Schrodinger bridge, it admits the following structure. So this is a distribution, okay, on path space, such that where you can rewrite it as the bivariate distribution of x0 on xn pi star s on s is here for static time on the conditional distribution of all the remaining states x1, x2, xn minus 1 conditional upon x0 on xn. It has to coincide with the conditional distribution of the pace process. Okay, so it's really simple identity. You just write down essentially the KL discrepancy, and it's obvious that this is really what the conditional distribution of the kind of intermediate state should look like for pi star. Okay, so now really you don't have to solve this kind of problem on path space. You could think of it that the only thing you need to solve is to solve really the problem for this kind of bivariate distribution, which can be rewritten simply as follow. Okay, so it doesn't seem that it makes you have made much progress here, where h here is the entropy of this bivariate distribution. But what one can see is that if I were using for a base process a simple random walk, this thing is nothing but the so-called, entropy regularized optimal transport, which has been popularized, particularly in machine learning, by Markov Chain. Okay, so you can think that there are actually strong connection with what we're doing currently on this so-called entropy regularized optimal transport that is now very commonly used in the machine learning literature. Okay, so what we're doing really is that we have some kind of regularized Wasserstein to cost, and it's regularized by the entropy of my bivariate distribution, my coupling pi s star. Okay, so that's nice. I'm doing an introduction to this kind of Schrodinger problem, but I haven't told you yet how to solve it. So, okay, it's nice. It would be nice to be able to do that, but the question is, how do I obtain, how do I approximate this kind of Schrodinger problem? How do I find pi star? So what we're going to do is use an algorithm that has been developed for a long time in the literature. So that was, to the best of my knowledge, this was first proposed in 1940 by Robert Forte, okay, in France. And it has been rediscovered many, many times in the literature, in particular by Kullback in the statistics literature. It's known in this literature as iterative proportional fitting, or in linear algebra is also known as the so-called Sinkorn algorithm. Okay, so what this algorithm does is somehow iterated projection. So remember what we want to solve. The problem we want to solve, the original Schrodinger problem, is a problem when you want to minimize the kernel, okay? And you have two constraints. Constraint at time 0, you want the marginal at time 0 to be equal to distribution of the data, and the marginal at time n to be equal to this multivariate standard normal distribution. Okay, so here, iterative proportional fitting is just iterative algorithm that just enforcing only one of these constraints at each iteration. Okay, so at odd iteration, you essentially constrain the process to have as terminal distribution the multivariate standard normal, and at even iteration, you constrain the problem to have its initial distribution equal to the distribution of the data, and you can show, and the regularity assumptions are fairly weak, that if you iterate this projection, it converges toward the Schrodinger bridge problem. Okay, the solution to the Schrodinger bridge. Okay, so now what we're going to have is have a look at how these iterates, how do they look, and is there a way to approximate them numerically? Okay. So we initialize the algorithm by starting essentially calling the iterate pi naught equal to p, the kind of base process. Okay, and now I just want to implement the first step of IPF. Okay, so what do I need to do? Well, I need to minimize pi1 is the minimum of the kernel between pi and pi1 subject to pi n, its marginal at time n to be equal to standard multivariate normal, where it's trivial to see by another simple decomposition of the kernel that pi1 is somehow a backward process or reverse time process, which is such that which you can write as follow. It is a process which at time n, you have a marginal distribution with PRF, the standard multivariate normal, and then you basically have some backward Markov transition kernel, which has essentially the reverse time of the forward dynamic, okay? But it should, ring a bell, because really what standard score-based or denoising diffusion model are doing is actually, they're just considering this process. Okay, so what you can think is that standard denoising diffusion model, also known as score-based generative model, well, you can think of them as just doing just one iteration of IPF and stopping there right away. Okay, and that's their generative model. What I'm telling you is that, well, that's not going to be good enough, because if turned out that the marginal distribution of extent under P was very far from PRF, just doing one iteration of IPF is not going to convert toward anything that is close to Schrodinger bridge. So what you need to do, you need to iterate. So what's the next iteration? Well, the next iteration is, well, this time you have to solve this scale minimization problem under the constraint on the initial distribution of the data. And it's easy to see once more by using a simple decomposition of the kernel that it gives you somehow the next iterate of IPF pi2 is a forward process which you initialize at the distribution of the data, and it has forward kernel, which are essentially obtained by reversing the backward kernel of pi1. Okay, so pi0 was a forward process, it was P. Okay, so what you do, pi1 is a backward process that you initialize at pref, and you obtain the transition kernel by reversing the forward process. That's pi1. Pi2 is a process where basically the forward process that you initialize at the distribution of data on the forward, which are forward transition kernel, which are obtained by the essentially the reverse time of the backward process, the backward kernel of pi1, and so on and so forth. Okay, so essentially you alternate this forward and backward process. On each time, you modify the initialization and you reverse the dynamic. Okay. So in continuous time, you can really think of it as doing IPF in continuous time is what at odd iteration, sorry, you have backward process, backward diffusion, which are initialized at the Gaussian distribution. And at even iteration, you have forward diffusion, which are initialized at the distribution of the data. On the way the drift are related between subsequent iteration, it's just basically by simply the addition, by reversing the time, the sign in front of the drift, the previous drift, on adding a score term. Okay, so that's just kind of generalization of what we did in continuous time before for denoising diffusion model, but you iterate this process. Okay, you can show that this thing, if you could implement it exactly, that would converge to the Schrodinger bridge. Practically, we are not going to be able to do this, and we're going to approximate those drift essentially using this kind of core matching idea that I previously described. Okay. I'm not going to go for that, but essentially what you have to do at training time, you're not going to have to train one score network. You're going to have to train as many as you do Schrodinger bridge iteration, okay, IPF iteration, sorry. Okay, but the training doesn't have to be more expensive because you train it on a much shorter time. Literally, you diffuse many less steps than for regular diffusion. So it's not like the cost is actually more expensive in all the experiments we made. On that generation time, you just basically consider the last, essentially, neural net you estimate of the last reverse time diffusion, and this is your generative model. Okay. Okay. So to give you an idea, again, graphically illustrated on a two-dimensional distribution. So assume you have a forward process that doesn't take you anywhere close to a Gaussian distribution. First iteration of IPF, actually, well, it doesn't matter. I start from a Gaussian distribution, and I reverse the time. I reverse the transition dynamic to obtain at time zero something that doesn't look like the distribution of the observation. Doesn't matter. I restart from the distribution of the observation, run the process forward by reversing the backward kernel previously obtained, and I iterate like this to obtain finally my generative model. Okay, so this can be used for generative modeling, but it's more general actually. It can be used to do to obtain an approximation of the Schrodinger bridge between two empirical distributions as well. Okay, so here we found simple example where I have 2D data distribution. Here that would be I diffuse for only a small number of steps forward, so that essentially if I use just one step of like the standard denoising diffusion model, I obtain nothing that looks like the distribution of the data. because I haven't diffused enough so that marginally at time n, I had something that was Gaussian. But if I iterate I compute IPF and I compute an approximation of Schrodinger bridge, I'm able to obtain kind of generate a sample which are much more faithfully approximate the distribution of interest. Okay, so this is example here on Celebre. So that was done. So that wasn't done at DeepMind. It's work done at the university. So we had a budget of about £1,000. So that's not fantastic, but still we could actually get a result showing that basically we are able to generate pretty good quality sample using only 50 steps. Okay, which is actually reasonable. As I say, you can use that also not only to do generative modeling, but you can also do this to kind of interpolate between two empirical distributions. And this is what was done here. And also interpolating here between EMNIST and MNIST. Okay, and so on. So that's all the generative modeling part. I don't have much time to discuss the inference bit, so I will go quickly for it and just give you the kind of really main idea. So now the idea is to say, okay, so we have this machinery that does essentially kind of generative modeling. But in a lot of applications, we are not interested in generating, unconditional sample per se. There are very few applications where it matters. What would be kind of more interested is to do some kind of conditional simulation. So really, particularly, what you're going to have is that you're going to say, well, say you have access to CFAR10, okay? You have a likelihood function as well, okay? Given observation y-ups, you are interested to sample from essentially the resulting posterior P of X given y-ups, okay, which is proportional to the distribution of the data, okay, time, obviously the likelihood evaluated at the observed observation. Okay, so how could you tackle this problem? Well, you can think of this kind of generative model where somehow it defines some kind of implicit data-dependent prior, which are learned by some neural net, okay? And actually, I haven't had time to discuss that, but you can get really some kind of approximation of log P data pointwise. So you could use this, kind of generating modeling algorithm, approximate P data X, okay, and I say you have access actually to an analytic expression, and then combine that with the likelihood so as to into some kind of MCMC algorithm. And there are actually quite a lot of papers doing this. It's not great because it's extremely slow. Okay, but imagine that we are doing that on images. I have easily 100,000 dimensions. So you're back to having doing MCMC in really high dimensional space, and it can be problematic. And also, obviously, it's going to require having access to an explicit expression for the likelihood. Okay. So we say, would it be possible to kind of bypass that completely, and try to do everything in a simple algorithm, okay, and use this kind of Schrodinger bridge machinery so as to do a sample for an approximation to the posterior distribution of interest. Okay. So really, I would say, well, maybe what I could do is, remember my Schrodinger bridge, what he was doing, the original Schrodinger bridge problem. I was trying to solve a kind of K minimization problem between some distribution on path space pi and some reference distribution on path space p, okay, which was the distribution of the data, which is diffused forward using some kind of Einstein-Lindbeck process. But here, could we say instead that we solve the same problem, but instead of having for p the kind of unconditional distribution of the data that is diffused forward, it will be the posterior distribution, which is diffused forward toward some kind of Gaussian. And we solve this problem. Well, I can formulate this problem, but unfortunately, the algorithm I presented before is not applicable because the algorithm I presented before, it requires being able to sample from the two marginal constraints I have at time 0 and at time n. Well, when I was doing this kind of unconditional generation, it was simple because it just only required me to sample from the unconditional distribution of data for multivariate standard normal. But here it will require sampling from the posterior distribution of interest, which is what I'm trying to achieve in the first place. Okay, so that's not good. Okay, so what we're going to do, we're going to use an idea which I first saw used in Marzouk, in a paper by Youssef Marzouk from MIT, but it's been used also in other papers, actually quite a few papers in machine learning where this idea is used. It doesn't never be used in the context of Schrodinger bridge, but essentially what I'm doing is I've adapted this idea to the context of Schrodinger bridge, okay? And the idea is the following, okay? So what you're going to say, you're going to introduce distribution, you're going to do a transport, kind of like trying to solve the Schrodinger bridge problem between not two distribution on X, but on distribution on X on Y. So it's really literally what we're going to do. So the distribution on X on Y I'm going to consider is simply the joint distribution of the data times the essentially distribution of the observation given X. Okay, so I assume I can sample from the likelihood. On a reference distribution on X on Y, so I'm going to consider simply the reference for X, I'm going to put say multivariate standard normal. And for Y, I'm just going to consider the marginal distribution of the observation under the unconditional generative model, which is essentially I take data from the sample from the data, and I add some. I basically sample from Y given X. Okay. What Marzouk tells you is that if you can essentially build some kind of transport map, and this is really what Schrodinger bridge does, between two distributions like that, it's a map between, you don't only transport X, but X and Y. On the map on Y you've constructed is the identity that is literally Y stay where it was, okay? And it's possible because essentially the distribution, the marginal distribution of Y under these two joint distribution is the same. Then if you learn to do that, okay, then you just need to essentially later on impute literally your transport at the observed observation, okay, Y-ups, and that will generate sample from the posterior distribution of interest, okay? So this is really exactly what we're doing. So we're going to do essentially reuse exactly the algorithm we've used before, but instead of using it on X only, I'm going to have sample from the joint distribution XY, okay? I'm going to have sample from this joint reference distribution, and I'm going to use my algorithm to learn essentially the Schrodinger bridge between these two distributions, okay? And once I want to basically sample from the posterior distribution of interest, I just literally applied in my reverse time diffusion, instead of using Y, I use basically Y-ups, and that's it. And you can show that what this thing does, it solves some kind of average version of the intractable Schrodinger bridge problem I was presenting in the previous slide. Okay, so that's what it does. Okay, so that's simple. So you can apply that for filtering. I don't have time to do that to explain that, but you can use it for filtering. So in particular, you can do filtering for state space model in scenario where you can only sample from the latent state forward, and you can only sample the observation. It's some kind of super ABC, if you want. Okay. Maybe a kind of more, impressive application is for things related to things like super resolution or in painting. So I'm presenting you here an application to super resolution. So this is the true image This is the corrupted image you obtain, okay, yeah, in those two rows, in those two columns, sorry, here, okay. And then what I'm presenting around here are sample from approximate sample from the resulting posterior, okay. What you should keep in mind is I only did the training once, and for all basically observation, I use exactly the same algorithm once basically it's trained, okay. So I don't need, once I've done the training, I don't need to basically to ever revisit the training procedure. I just feed my observation, and this is the sample you obtain. So here we know over 100,000, dimension. For example, it's quite fun here. So, for example, for this example here, you can see that it proposed people who have glasses, wear glasses or not. And this is pretty high quality image, whereas it's done actually only at universities. So it's actually pretty poor. We don't have like pretty powerful computational access to computational resource, powerful computational resource. Okay. So just to summarize, so there's this really nice class of generative model that have appeared recently, the class of Denoising diffusion model. So what we did, we obtained some like I think the first theoretical result for this class of model, which kind of explain why there's no mixing issues when you use those techniques. You can improve this kind of techniques and speed them up by using some transport idea, the so-called Schrodinger bridge technique. And we propose a way to approximate the Schrodinger bridge by approximating the iterative proportional fitting estimate using score matching. And finally, you can extend all those ideas so as to do conditional simulation. Thank you. And if you're interested, the two papers you can have a look at are this first paper and this third paper, which are the two papers where we do unconditional and conditional simulation with Schrodinger bridge, while the two papers at the bottom are the kind of key, reference on denoising diffusion model.
Arnaud, thanks a lot. That was super interesting. Is there any question from the audience? It's not time to type your question if you have one.
Sorry.
I was wondering myself, I'm not very familiar with generative models, but my understanding is often many methods you define a base distribution or reference distribution, which is low dimensional, and then you try to learn a function towards a large dimensional space. In your case, the dimension has to be the same, or could you do something to make it smaller or larger?
So in the thing I presented, it's indeed the same. So they've been method that have been proposed where people actually goes from some kind of reduced dimensionality and then use some kind of decoder that takes you to kind of higher dimensional space, the original, say, data space. Yeah.
Okay.
So that has been there's a lot of papers on the topic at the moment. So there's been papers like that that have been proposed. Yeah, sure.
And how does it work exactly? Is you just you have a kernel from one space to another, they're just different?
Yeah, they kind of, you consider latent space, you do the diffusion in latent space, and at some stage you have a decoder that takes you back to the original space, basically.
Oh, okay. Fine.
So there's been a lot of kind of, so in particular, I don't know if some of you might be familiar with so-called implicit function representation. So in this case, you kind of approximate your image by a function, and you can think of the pixel as instantiating essentially this function in the domain. These functions are represented by a multi-layer perceptron, and you do diffusion in the space of the neural net coefficient. You can do it in Fourier space. There's been quite a few things. These ideas as well have been exploited, actually.
Okay, thanks. We have a question from Dong, but Dong, do you have a microphone or should I read your question? Because I remember last time you didn't have one, so.
So yeah, I see the discussion of Deng. The thing which is important Deng, is that we do more IPF step, but it's only at training time. At generation time, we just do one step. We just train the neural net. So the IPF is just at training time for the neural net. When you finish your training, you have access to essentially a time reverse diffusion, which is basically typically require less time step than the original denoising diffusion model. On at generation time, you only need to simulate this short time reverse time diffusion. Okay.
A very good point. Thanks
so can it become arbitrarily short? The answer is no. On the answer, no, there's no miracle, obviously. It's simply because essentially it's related to the fact that we are approximating the Schrodinger bridge, the true Schrodinger bridge diffusion. If it turns out that this diffusion has very, sharp drift, or in particular, even the iterates, during the iterates, your iterates have really sharp drift, then you would need actually quite a few time steps to have a decent approximation of it. So there's no miracle. At some stage, you're limited by essentially how steep the true IPF iterates on the final Schrodinger bridge solution, how steep it is. So practically, obviously, we don't have access to the true iterates. Okay, so there's no miracle. We on the true Schrodinger bridge. So what we check empirically that we have a solution which is normal, and our approximation of the SD is not, is numerically stable. Yeah.
Arnaud, there's another question, but in the chat box from Xiwan Yu. Are the DSB iteration taken at each time step T in the diffusion? I don't know if you can see it.
So yeah, each iteration, so when we do our training, is really each iteration is literally doing alternating forward diffusion, backward diffusion, forward diffusion, backward diffusion, so on. So this is each iterates, each IPF iterate consider all the time steps. Okay, but I reiterate that this is only at training time. At generation time, when you've trained your model, you do as a standard denoising diffusion model. There's no additional. There's no need to iterate through this IPF iterate. IPF iterate is only at training. Could you say on what space are the arguments taken during the IPF iteration? Oh, sorry. So it was respect to pi. Okay, so I should have precised in my slide. Sorry, just give you an example. So here, I look at all so this is over the distribution pi on path space. Okay, so over all the distribution on pi on pi space, on path space, sorry, I look at the one here, for example, that has the minimum care discrepancy with respect to pi1, conditional upon this distribution having as marginal distribution at 0 the distribution of the data. So yeah, I should have a pi here to be clear, actually, sorry.
Arnaud, we have another question from Adrien. Maxime, do you think you can open the microphone of Adrien? Or?
Yeah, we'll unmute Adrien. Okay.
Okay. Yeah. Thanks, Arnaud. Hi.
Hey, hi, Adrien.
Yeah, it's been a while. Yeah, it's actually a follow-up question on what Deng asked about, like the drift that you get from your score model. the score of your model, like that can be sharp, but I thought there had been work on like regularizing the drifts in generative diffusion models, somehow like penalizing the total like the total variation norm of the drift across the
so
path.
they did it for I think it was Fjord that was using that, but that was a bit different. That was in the context of kind of normalizing flow with ODE. If I remember well, they were indeed kind of regularizing it by the kinetic energy, so as to have drift which are not too widely. But here it's not really the problem we're having. I mean, you could kind of regularize them, but then you would have, I think, no guarantee that you would converge towards the Schrodinger bridge. Because what I think here the problem is that the true Schrodinger bridge could have a very sharp drift. So if you consider, for example, two distribution with very distinct support, really, you know, you consider very, very short time, well, the drift will have to be steep to go from distribution pi naught to pi 1. There's not going to be any miracle. So there will be an issue here.
Yeah, no, okay.
Sorry, any other question from the audience? No.
And you can apply it to filtering, which is the pardon.
I did not really understand the point of the gamma k at the beginning. Is it like to slow down the or to yes?
Yeah, you don't want to go to so the gamma k are the discretization of the SD actually. So okay. Actually you can think of it. We write everything in continuous time and then we discretize. And it turned out that it actually makes sense not to use a fixed step size actually.
Okay, that's right. Okay, so.
Yeah. So I may skip the detail because it's a bit hairy, but yeah.
But you slow down progressively. You don't accelerate, right? It's you make.
No, exactly. You slow down progressively. Yeah.
Okay, that's.
Well, actually, so it depends in which sense. When you're close to the data, you have to be very, very careful. And when you go towards the Gaussian, it's much simpler.
It's a bit like tampering then. Okay.
Yeah.
Okay.
Yeah.
That I understand then. Because the notation suggests something a bit like Robin's Monroe, but
no,
it's something
sorry,
else.
No, it's not. Yeah.
Okay. But yeah, it's a way of slowing down or accelerating the diffusion. Okay.
Yeah, exactly. Yeah, exactly.
Well, I don't see any other question. So let me from everybody, let me thank you. Oh, wait. Dong has another question. I don't know if you can read it, Arnaud.
Yeah. There's some kind of similarity between GIFs and Posterior. So I don't know of any theoretical result connecting the two. It might be worth looking at it, actually. In the Gaussian case, what is sure is you can, I mean, for IPF, and we have the calculation in our paper, and we are not the first to do it, is we have the exact update of IPF. So you can study actually the rate of convergence of IPF very kind of precisely when you're in the Gaussian case. But I mean, I don't know really what kind of, theoretical result would be connecting the two. Might be worth looking at it. Yeah.
Same kind of linear algebra for Gaussians at least.
Yeah.
Okay, I think it's time to stop. No, wait, one more question. No, it's Dong saying thank you. Okay. Well, thanks a lot, Arnaud, for the interesting talk. Thanks for the audience. And so we meet again in Maxime in 2 weeks or 3 weeks, 17th of May?
Yeah, 3 weeks, yeah.
In 3 weeks for a talk by Darren Wilkinson. So stay tuned. And thanks again, Arnaud.
Okay, thank you, bye.
Thanks, Arnaud.